In the laboratory for household robotics, we are concerned with machine vision, dynamic world modeling, and mobile robot navigation. In one of our first projects, we developed a navigation system for a personal robot based on a rotating ultrasonic ranging device. This robot, named the Intelligent Mobile Platform, or IMP, could learn the floor plan for a house and then navigate within the house in response to commands, such as go to the kitchen. The IMP used its rotating ranging device to maintain a dynamic model of its environment. This model permitted the robot to learn the house floor plan, to detect and avoid obstacles, and to maintain an estimate of its position as it traveled. More recently, we have developed a navigation system for an autonomous mobile security robot. The security robot employs a ring of 24 Polaroid ultrasonic ranging devices in place of the rotating focusing horn. This sonar ring permits the robot to scan its immediate environment several times per second. Like the IMP, the security robot executes task-oriented commands of the form go to place, where place is a pre-learned location in the robot's model of the world. The navigation and dynamic world modeling techniques for the security robot were developed using an interactive mobile robot simulator. At the bottom of the simulator screen is a floor plan in which the robot can move and sonar signals are simulated. Goals are communicated to the robot using a mouse. A simulator window is used to graphically show the free space detected from each sonar scan and the robot's interpretation of sonar signals. The results of each scan are projected to world coordinates and connected to form a polygon named sonar horizon. Any local goal for the robot must be within its sonar horizon. The sonar depth readings are converted to line segments, which are shown here as thick lines. These line segments are used to build up a composite model of the robot's local environment, called the composite local model. The composite local model can be augmented by line segments that are recalled from a previously learned global model. The composite local model is used to guide learning and local obstacle avoidance. Matching the line segments from each scan to the composite local model permits the robot to detect and correct systematic errors in its position or orientation. These errors permit the robot to overcome the effects of wheel slippage and to maintain an accurate estimate of its position as it travels. The position error detection is illustrated graphically by the thin and thick line segments which are projected perpendicularly to each line in the composite local model. Each match provides a vector of position and orientation error. This error vector is used to correct the robot's estimate of its position. A dialog window is used for text messages and for entering commands to the IMP. The robot can be made to learn a model of the world by placing it in learn mode. In learn mode, the robot learns a network of named places connected by legal highways. Each place is given a name. The robot also learns a global model, which tells it what surfaces it should expect to see from each place. In learn mode, the robot follows walls using a set of pseudo-sensors, which we call whiskers. When learning, the robot stops every 2 feet to take a clear picture of the world. Although the sonar sensor is used while the robot is traveling, the sonar signals are cleaner if the robot is stationary when the scans are made. At each place where it stops, the robot tests to see if the wall is still to the right. It then computes the coordinates of its next place and tests to see if there is a free path to this place. If the path is blocked, the robot will begin to follow the wall that blocks its path. After computing the next goal point, the robot tests to see if there is a free path from the last place learned to the next place. If there is not a free path from the last learned place, or if the distance is more than 10 feet, then the robot learns a place at its current location. In automatic mode, the robot is given commands of the form go to place, where place is a learned, named location in the network of places. This network provides a set of known places which serve as decision points for global path planning and provide the robot with local goals for local navigation. Global path planning provides a list of goal places through which the robot must travel to reach the named place. The robot travels a path as a sequence of straight-line movements. At each known place, the robot turns towards the next place on the path. After verifying its location, it then proceeds to the next goal point. As it approaches each known place, the robot recalls an expected local model from the global model, which it learned in learn mode. The simulator permits obstacles to be placed in the floor plan. The robot can detect an obstacle in its local model and plan a path around it. The avoidance path takes the robot to the side of an obstacle and then back to the next place on the path. The navigation system has been tested by replacing the simulated motion and simulated sonar signals with motion and signals from the real robot. This permits us to rapidly test and improve navigation and modeling techniques in an easy-to-use programming environment before the programs are recorded to run on the onboard processor of the robot. We are now very close to the point where the entire navigation system can be run on the robot's onboard computers. This will allow the security robot to be both intelligent and autonomous. We are currently working with the Civil Engineering Department to demonstrate navigation in a coal mine environment. Intelligent navigation will open a large variety of applications for robots in the future.